Well, good morning, Beatrice. Good morning, Kate.
Good morning.
Kate, I sent you a message back about that problem. It was just an issue with the rounding. I gave you the points back for it, but it didn't want all the decimals it listed. It just wanted that last one rounded up.
Okay, I got it. Thank you.
Sure. So what have you two been working on in terms of 8.3? You read through it, any particular parts of it you're playing with or fighting with?
I got through to question 5, and then I just stopped because I was going to finish it these next few days, and I was a little confused on the vectors and how it worked.
Okay. Beatrice, what about you?
I'm still on the process of reading the book right now.
Okay.
I'm still reading the lesson on the book.
So you might have noticed, as I warned you guys about last week, that section is quite large.
Mm-hmm.
And there's a lot to it, mostly in terms of notation and vocabulary, and just kind of the idea about what is a vector. And we're used to, in mathematics, our variables standing for, numbers. So like an X might be the number 5. Whereas when we start talking about vectors, vectors are still like numbers in that they are a quantity, but they are a quantity that have multiple pieces to them. So one of the things that your book talks about is when we want to write a vector, we put that little arrow on top of it. That arrow just says, hey, this is a vector that we're talking about. Some textbooks and in both math and physics and engineering will instead sometimes change from a number or a letter V to a bold V or a bold whatever letter they happen to be using for that vector to say, hey, I'm bold, I'm a vector instead. And that's kind of, it's unfortunate that they still do that sometimes. It comes from a period where trying to get the little arrow over your letters was either difficult or annoying to do in typeface. But nowadays, of course, you can just put a shortcut key on your keyboard. You hit Control V and it comes up with a little, or Alt V or whatever you want to map it to, and you get a V with an arrow instead. So it's so much easier nowadays. They really should be putting those arrows on everything, but sometimes you'll see them written as bold instead. But the difference between what we normally think of as in quantities as just being numbers, in vector, you have a quantity, and it still is a single quantity, but it has 2 characteristics. It has a magnitude, say 10, in a particular direction. So 10 units going, I'm going to use the generic term going, 10 units going, I don't know, I'm just going to say east. It's got both a magnitude and a direction associated to it. One of our most common kind of default examples of a vector is velocity. So a common example will be velocity. And when you talk about velocity, you talk about it's not only how fast something is moving, but also how fast and what direction it's going. Versus talking about speed, where speed is just how fast. Fair. Other common examples of vectors are things like force. You know, if you've got some object that's being pulled, there's a difference between pulling it with 10 pounds of force in this direction versus pulling it in with 10 pounds of force in that direction versus pulling it with 10 pounds of force in that direction. Not so much longer. So when you're talking about things like velocity and force and acceleration and things, you know, very physicsy kinds of stuff, a lot of these quantities want to have something else to distinguish them. They want to have not only how large is this quantity, but what's its orientation. And we actually do have a version of that that we've been using for our, you know, normal numbers. When you talk about the difference between, say, the number 5 and the number -5, we often think about those values as going in different directions. A +5 goes this way, where a -5 goes that way. So a lot of the things that we do with vectors are going to be very, very similar to things that we do with numbers in terms of signed numbers. The big difference is, instead of just being able to go two directions, the positive direction and the negative direction, we will be able to go any direction that we want. Not only in 2 dimensions, but in 3, 4, 5, however many dimensions you want to work with. We'll be able to handle things going in various directions. Now, most of the examples that I've talked about so far, and most of the examples in our text, are fairly physics-based, but this type of thing, vectors in general, are used a lot in other fields as well, in finance and in sociology, in studying lots of things. Vectors are used. Even things that seem as non-mathematical as, you know, shifts in public opinion. Public opinion will shift by a particular degree and towards a particular set of opinions. That's a direction, that's a magnitude. We can express them like vectors. As you started reading and started playing with this, you saw the first way we, as a, you know, species, started representing vectors are kind of exactly like I did here, as a directed line segment. So we draw our vectors in such a way that their length represents their magnitude, or is proportional to their magnitude in some way. So if this vector was 10 pounds of force, and I wanted to have something pushing back on it, like say friction or something, with 5 pounds of force, that 5 pounds should be half the length of this 10 pounds. So we represent those vectors in terms of their magnitude, how large they are, in terms of that length. And of course, the direction we imply by having it point in that direction versus some reference. So we might measure from standard position like we have been. We might measure down from north if we're doing, say, navigation. We might, you know, measure it from any given reference point. For those of you who go off and do physics later on, one of the first things you do when you're diagramming out a problem is you know, will at some point list on the problem, that is the direction I'm calling down. So that's the direction of my gravity. So everything else can be measured off of that. And then, you know, you'll just transfer that vector so you can measure all of your angles versus that same reference point. Is one of the fun things when you start doing a lot of physics. You know, why did you call that way down instead of this way down? You can call any direction you want down as long as everything is measured the same from it. So you just need to talk about direction. You just need a reference. Make sure everything is based on the same reference, and it doesn't matter what direction that reference is. Now, there's a couple of questions that in the beginning of 8.3 about taking this idea of just sketching vectors as directed line segments. So line segment, because it's only a finite length, where that length again is proportional to its magnitude. And it's directed because we do consider one part to be the tail and one part to be the head of the vector. So it is going in a particular direction. There is a difference between a vector pointing in this direction and a vector pointing in that direction. They're opposites of each other. They will cancel each other out. So we do have the arrow only on one side. And while it is possible and was done for literally thousands of years to diagram out a set of either movements or a set of forces by just drawing the different vectors out and adding those vectors together. Your book talks about the tail to head method. So we could just draw these vectors out very, very carefully and then add them together graphically very carefully and figure out that the sum of our vectors, u plus v plus w, was this new green vector. I'm just going to call it r. And if you needed to figure out what the sum of all the forces or the sum of all the movements was for whatever you were happened to be doing, you would literally draw them out very carefully at very precise angles, measured very precisely, and then would draw those resulting sums and then physically measure the angle it ended up at very carefully, measure its length very carefully, and use that as your calculations for whatever you're constructing or however you're trying to navigate towards things. And it actually works fairly well, but takes a fair amount of precision in how you graphically draw things out. But eventually, as math got a little more, math and engineering and physics got a little more particular, a little more precise, and after the mostly the work of René Descartes to combine geometry and algebra, we started wanting to take these vectors and put a little bit more algebraic and kind of numerical rigor on them so we wouldn't be so dependent on a very, very precise drawing. So what was done? Well, we put these vectors into kind of our Cartesian coordinate systems and defined a couple of special vectors. Now, your book doesn't go too much into this notation, but it's a really important notation for you to know. So I want to make sure you see it. Defined two special vectors. The first one being a vector I. And you'll notice that I has a little, instead of having an arrow on top, has a little hat on top. That hat is a technical term. It is I hat. The little kind of chevron on top is a hat. So it is I hat. I hat is defined as the vector of magnitude 1 in the positive x direction. And it is read I hat and it is a, being magnitude 1, it is often referred to as a unit vector, because it has a magnitude of 1 unit. So that's the first special vector that we define. The second special vector we define, you may be able to guess, is a unit vector in the positive positive y direction. And that's j hat. Y, I, and j? Oh, actually, no. Why not y and j? So it's a unit vector. Again, that just means its magnitude is 1 in the positive y direction. Now, why do we define these two special vectors? Well, as soon as we have these two special vectors defined, we can define any other vector in terms of I and j. So if we want to take this black vector v and have a way of describing it that we can use our kind of algebra tools, our nice numeric tools on, we can define it by looking at, okay, how many i's does it take to make that vector? This looks like 1, 2, 3, 4, 5 i's. So 5 i's. And then it would take what looks like 1, 2, 3 j's. So plus 3 j hat gives us a component form for that vector. Essentially, it makes that vector out of building blocks. Fair? And let's say we had another vector. W. Now, notice I drew that vector W head to tail to the vector V because we're going to add them together. But one of the big things about vectors is vectors, as I said before, they have a magnitude and they have a direction. They have how big they are and what direction they're going. They don't have a position. They don't have a place. We could draw that vector W anywhere. And as long as it has the same length and points in the same direction, it is the same vector. Fair? So if I want to add them together, it might be handy for me to put W right, well, that was a little stronger of an angle, but that's okay. Put vector W here, because then the coordinates of where that head is will tell us how many i's and how many j's. Or it might be nice to put that vector W up here so that visually representing their sum is a little bit easier using that head to tail method. Either way, it's the same vector W. Fair? And if we wanted to figure out what its components were, well, it's -1. I'm going to just say that's down 2. It could be 1.5. It could be 1.9. It could be, but whatever it happens to be. I want to say that's -2 though. So down 2, -2 j's. Negative because those j's are going downward instead of upward. And then 1, 2, I'm going to say 3 in the I. gives us the component form for that vector. So if we wanted to add these together and find that blue vector, which I'm going to call U, V, and W are probably the three kind of standards for vectors, but they can be anything. If we wanted to find what the component form for that blue vector is, just add them together. V plus W is going to be 8 in the I hat. It would take 8 I's to get all the way out to here, plus 1J. Okay, my scale's a little off. That's okay. 1J to get up there to its head. So doing our adding and subtracting and even some of our multiplying with vectors in component form it's real nice, real easy. Fair? Now, some of the tricks, we'll get back to this question, or we might get back to this question. I was just had that as an example, so we could, let's just look at it real quick. If we wanted to figure out, say, how to build vector R out of the vectors that we have here, out of vectors U and V, well, R looks like it might be, well, it's almost the opposite. If we took V, the opposite of V would go that way. So that's a negative V. But we want to end up here. So, I don't know. Maybe I picked a hard one. Negative V would go that way. What about V minus 2U? So if we took V and then minus U, so that's V, and then minus U minus another U, that would give us R, right? So this V minus 2U, again, V is a vector that goes that way, because that's what they tell us V is. And then minus 2U, that's a minus U. That's a minus U. So that would give us a resulting vector from this tail up to that head. And that looks a lot like R. Fair? That's all that question's asking you to do. How do we make some of these vectors out of other vectors? Like this T. A T has a lot of horizontal to it, so it's going to need a bunch of U's. But then it does have to go down, so a bunch of U's and a little bit of negative V, so a bunch of U's and a little bit of negative V. If you were to draw it out nicely, I bet that T lines up exactly with 3 U's and then back with V. It takes a little while to get used to kind of seeing that, but with a little bit of practice, you'll start to see it. So one of the first things that we have to be able to do to get these kind of two ideas of magnitude and direction and component form to talk to each other is we've got to be able to take a vector that has, say, a magnitude of, I'm just going to use 10 units. And again, it could be 10 feet, it could be 10 feet per second, it could be 10 pounds, it could be 10 anything. And a particular direction, in direction, let's just say 30 degrees up from positive X. So I could have just said 30 degrees standard position. So that's 30 degrees. If we wanted to turn this vector from being told how long it is and what direction it's going. If we wanted to turn that into component form, and that's our ij form is a type of component form. We'd need to figure out, well, how many i's is it and how many j's is it? That means we'd have to know how long is it in the x and how long is it in the y. Well, we've been doing things like that for weeks and weeks, right? We know that this x value, we associate the x value with the cosine of that angle. Now, the cosine of that angle is going to equal that x value over the radial value, right? So this actual x value here is going to be 10 times, if you multiply that out. So it's going to be the magnitude times the cosine of the 30 degrees. The y value is going to be 10 times the sine of that 30 degrees. Fair? Cade, is that fair?
Yeah.
Okay. But we've been finding those kind of lengths for a long time. So this green vector v here, if we wanted to write it in our ij form, would be just 10 cosine 30 degrees in the I and 10 sine 30 degrees in the j. Now, if that wasn't a nice 30 degrees, we get decimal approximations for those to any decimal value that we want. If we needed to stay exact and it wasn't something nice like 30, we could just leave it. Like if it's 10 cosine 35 degrees, that's an exact value, we could leave it. But we know what the cosine of 30 degrees is, so we might as well turn that into 10 times the square root of 3 over 2 in the I and 10 times 1/2 in the j, or 5 square root of 3 in the I plus 5 in the j. Cool.
Yeah.
Now, it can be a little bit more difficult at first to do that if we're not given the angle in standard position. So for example, if we had been given this as, say, 60 degrees and measured, say, from, I don't know, north, because we were talking about navigation, and we had drawn this out with that as north and that as 60 degrees, we could use that 60 degrees, but it would make the cosine 60 degrees this adjacent side and the sine 60 degrees this horizontal part, the opposite of that angle. So if we use an angle from a different reference, we'd have to change which ones our sines and cosines are. So often, to kind of avoid that, it's common early on to just turn everything into standard position. Take whatever information you're given about your angles and just turn it into standard position so we agree with what we're used to. Fair? You know, our cosine is only our horizontal if we're defining our angles in standard position. Our sine is only our vertical if we're defined in standard position. If we're not defined in standard position, they can be, well, anything, depending on what we're measuring from. So some people like to put everything in standard position. Some people like to use the given references and adapt the trig functions. Either way, you're going to end up with the same vector. It's just going to look a little different. So careful about that. So we've got to be able to go from a direction magnitude form of a vector and turn that into component form. We also need to be able to go from component form and figure out what our magnitude and direction are. Now, we'll do that in a second, but before we do that, I want to note some of the notation that your text uses a lot. I think it uses it too much, but yeah. Because I drew this vector from with its tail on the origin, this it has a particular name. A vector drawn with its tail at the origin is referred to as a position vector because the vector's components point towards this location, that little XY location in space. Fair? Remember, we could draw this vector anywhere that we wanted to. It's just often handy to put that tail at the origin. And the coordinates of that XY point, we know the coordinates of that XY point because we know this goes over 5 square root of 3, and we know it goes up 5. Right? Because we know that's the amount of horizontal and vertical displacement we have. So it's very common to express a vector that is in position vector placement. Instead of defining it based, instead of using the notation with the i's and the j's, we just use the coordinates of that head if it was written in position form. So you'll see it often just written as 5 square root of 3 comma 5. Notice the brackets, they're not parentheses. It's not that point in space. Up here it's parentheses because it's denoting that ordered pair, that point. Here it's got these angled brackets. You can use the greater than, less than symbols to type it to express the location of that head. There's really mechanically very little difference between those two forms. To be formal, and people are getting a lot less formal, and your text is less formal than I would like for this. This first form, the IJ form, is what we would call component form in a formal application. This form is position vector form, or written as a position vector. But people don't like writing a lot of extra stuff. So a lot of people like writing that position vector form instead of writing out all their i's and j's all the time. And it can be handy, don't get me wrong. I use position vector notation a fair amount. But the IJ notation does have some advantages to it, and we'll look at some of those advantages. Frankly, actually, we already have in some ways. If up here, when you talk about given this and adding that, the idea of adding like terms is fairly sensible. If you see 3i minus 2j plus 5i plus 2j, that doesn't look all that much different than, say, if it was 3x minus 2y plus 5x plus, what did I put in? It should be a 3, sorry. 3y. And how would you add that together? You would just add like terms, just like we do with our vectors. So your algebraic kind of intuition likes IJ form, or true component form. But if I went down here and said, hey, take 5 and say 5, 3 and add it to 7, 4, you wouldn't necessarily look at that and go, oh, clearly that should be 12, 7, because your intuition tells you that in some way. Fair? So, or when we start multiplying and I say 3 times this, weird notation to square root of 7. If I wrote this, you go, okay, what can I do? What can't I do? Versus writing 3 2i plus square root of 7j. Well, this looks a lot like if it was 3 times, 2a plus, 7b, you would just distribute, right? Well, you can distribute here just like you would up there. The fact that you can also distribute here is not trivial. This notation doesn't say, oh, we should be able to distribute multiplication over addition, because you can't see the addition anymore. Fair? So it's a handy notation because it's a nice little shorthand, but it does remove some of the mechanics. So it does have some disadvantages while people are learning. So just something to keep in mind and be careful. Though your text in the online refers to both of them as component form, for those of you who go on and do a lot of physics, you'll actually often use what's called the matrix form of vectors. There's lots of different forms of vectors. It's common when something is as useful as vectors. So just a little bit of notation and vocabulary there. Okay, I don't want to get too far off here. If anything comes up, by the way, that you want to ask about, I'm just kind of giving you an overall spiel of some of the pieces and mechanics and vocabulary here. So if anything particular jumps up that you're like, oh, I want to see more about that, let me know, okay? Okay. So let's say we're given a vector in component form. Let's say it's, 5i, man, how about minus 3j? I want minus 3j. No, I want minus 5i plus 3j. That'll be more fun. So minus 5i plus 3j, it's going to be minus 5, 1, 2, 3, 4, 5, up 3. So it's going to be about there-ish. So that's our vector v. And somebody asks us, what is the magnitude of v? And similarly, they ask, what direction is v going in? So we should be able to answer both of those questions. Now, again, the magnitude of v is supposed to be proportional to its length. So magnitude is just a fancy way of asking, how long is that thing? Fair? We have a notation for magnitude of v. It looks kind of like absolute values, but it's a double barred absolute value. So that's read the magnitude of v. Magnitude of v. The nice thing about the magnitude of v is, well, what do we know? We know this length is -5. We know that length is 3. We know that that forms a right triangle. If only we had a tool to find the hypotenuse of a right triangle, knowing the two sides. Do we have such a tool? What tool is that?
Can you use I forgot what it's called. It's like we just did it in 8.3.
Oh, 8.2. We could use law of cosines, true.
Yeah.
But it's a right triangle, so we don't need law of cosines.
Pythagorean theorem.
Good old Pythagorean theorem can handle it.
Oh. Oops.
Now that would give us the square of the magnitude, but since we want it to be positive, all magnitudes are positive, we can just take the square root. So it would be the -5 squared plus the 3 squared's square root. That's going to give us magnitude. And if you did use law of cosines, because this is a 90-degree here, that cosine of 90 degrees will be 0. So the back part of law of cosines would fall off, which just gives you Pythagorean theorem. So even if you did use law of cosines, it would still work. But yeah, it's really just a Pythagorean theorem application. That's one of the fun things about this chapter, or sort of fun things about this chapter, is that it will do things like present you with, here is the new formula for the magnitude of a vector. You've never seen magnitude of a vector before, and here's its big formula. And eventually somebody goes, wait a minute, isn't that just Pythagorean theorem? We've been doing Pythagorean theorem all year. Yeah, it's just Pythagorean theorem. Just in fancy vocabulary and new notation, but it's just Pythagorean theorem. That's it. So what is the magnitude of this vector E? Square root of 25 plus 9. So the square root of 34. That is the magnitude of that vector. What direction is it going in? Well, what direction it's going in, or how we list what direction it's going in, depends on what we want to use as a reference. Our basic reference is standard position, so we might kind of by default use standard position. But if for some reason we wanted to just find what's its direction down from upward, so we say we were trying to come down from north and we define north as upward, or we could define it in terms of, you know, this little angle from here if we wanted to. So we could find it from any reference that we wanted to find it in reference to. We'll do standard position just because it's kind of our default. What direction is it going in standard position? But again, we essentially have these two lengths associated with our angle. We have an adjacent side and we have an opposite side, or an x and a y. We have a trig function that relates angles to opposites and adjacents. We have a trig function that references angles in terms of x's and y's. It's our tangent function. The tangent of that angle in standard position will be the ratio between the y and the x. Or in this context, the j component over the I component. You'll see your textbook often say things like, for V given as AI plus BJ, or they'll even just go AB in position component form. And they'll say, they'll reference that the tangent of the angle is B over A. And again, they'll say that as if that's something new, some new formula just for vectors. It's not. That's how tangent has been defined since week 1. Just as, you know, with different labelings. So for our purposes, the tangent of theta is equal to b over a. That's going to be 3 over negative 5. Or just negative 3/5. That seem reasonable? What tool are we going to have to use, or what are we going to have to do to this thing to figure out what that angle is?
Would we have to do tangent inverse?
You will.
Inverse-
Absolutely. Tan inverse. Tan inverse. And what do you get when you find the tan inverse of that?
I get negative 30.96.
Ooh, negative 30.96
Degrees. Would be degrees, right?
degrees. So you get negative 30.96 degrees.
Victor's? No. I don't know.
This is always fun. When we use an inverse function, how many answers do we get?
2.
2 plus all the terminals, right?
Terminals, yes.
So for tangent, if you recall, we could just add half rotations and that would get us all those angles, right?
Mm-hmm.
Now, we have to do this, and you'll notice your textbook does not say that the angle is equal to the tan inverse of b over a. It doesn't say that. The reason it doesn't say that is then the only answer would be negative 31-ish degrees. Is this angle at negative 31 degrees?
No.
No. It's not, because this vector is heading into quadrant 2 and tangent inverse doesn't know about quadrant 2, right?
Mm-hmm.
It can't give us the right answer. But that doesn't mean that the tangent isn't equal to, negative 3/5. That doesn't mean the tan inverse that's solving this doesn't give us the right answer. As long as we remember, we get all of these answers.
Mm-hmm.
So the one we probably want is the negative, I'm just going to say 31 plus 180 degrees, which is what, 149 degrees? That's probably the one that we want. 149 degrees. Fair?
Yes. That's right.
But it would be just as accurate for us to have gone, say, with a -1 and said that, or the angle was negative 221? No, 211. Negative 211 degrees. From there, from here all the way around to there is that negative 211 degrees. Those are both in the same place, right?
Mm-hmm.
Which direction are we heading in? 149 or negative 211? They're both true.
They're both true, yeah.
Which one do we have to use? Either one.
Mm-hmm.
Which one do we tend to use? The 149.
Mm-hmm.
But what can we not use? The negative 31.
Negative 31. Okay.
Fair?
Yes.
Now, if that vector had been heading down into quadrant 4, we'd want to use the negative 31.
Mm-hmm.
So when we do this, we've got to consider the fact that there are multiple answers to this and make sure we're choosing one that is appropriate for our problem.
Mm-hmm.
Fair?
Yes.
And that can be a little bit weird. But yeah, you'll notice that's, and I'll catch a lot of people on this one. I'll say, you know, how do we find the angle? And they'll say the angle is the tan inverse.
Mhm.
And it's not. The tangent of the angle is the ratio. Because if you just say it's the tan inverse, then the only answer you get is that -31. It's the solving process that gives us all those other answers. Now, of course, that's me being very, very technical, but it's part of the fun of what I get to do is be very, very technical.
Mhm.
And it does make your plane go the right direction.
Mhm.
Let me see. What else do we got here? Let's see. That gets us 6. So yeah, some of those magnitude direction problems in 8.3 will do that. Like, just to show you, you got, you know, question 7 here. You'll be able to use the principal tan inverse because it's going into quadrant 1. Tan inverse loves quadrant 1. But down here, you're going into quadrant 3. Tan inverse doesn't know about quadrant 3. You're going to get a quadrant 1 angle and need to add 180 to it. Fair? So, you know, it's certainly going to do that to you. What else do we got here? Small plane lands at a point this far east and that far north. Yeah, so you're just turning it, you know, into a diagram. It's this far and this far. Okay, how far did it go? Well, what's its magnitude? What direction did it go? It's the same problem, just in terms of a particular metaphor. I do want to talk about multiplication in a bit. This question always scares people. Given these 3 forces, what are the sum of the forces? Well, guess what? You just add the forces together. Add those together, add those together. You know, it looks scary because, again, the visuals of the position vector form make it look a little bit like, well, how do I add those? But they're all just sums of forces anyway. So you just add like components. This becomes a subtraction problem. I'll let you play with that a bit. And these problems, I'll probably wait until Wednesday, let you guys fight with them a bit, but wait until Wednesday to play with them. The big thing I would recommend for these word problems is just draw. You know, start by going, okay, I got my plane going that way. I got my wind going this way. So my plane should end up going that way. Okay, find the vector for this. Find the vector for the wind. Plane plus wind equals what actually happens. Add them together. So make those nice drawings. But before I let you go, I do want to tell you one horrible, horrible thing. Actually, it's kind of cool, but anyway. You may remember, as you were being taught mathematics, you were shown 3 different notations for multiplication, right? You were shown this juxtaposition. The parentheses don't matter. If it was just 2x, you wouldn't have the parentheses there, right? The parentheses just stop it from looking like 23. But multiplication by juxtaposition, by just having them up against each other, multiplication implied by that dot, which is referred to as a dot product, and multiplication implied by this cross, It is not an X, it is a cross, technically, and referred to as the cross product. And you had these three different notations for multiplication. Did that ever seem weird? That there were three different notations for multiplication? I mean, we don't have three different pluses, do we? Well, I'll tell you, I'll let you in on the secret. There are three different notations for multiplication because they mean three completely different things. Unless you're talking about numbers. If you're multiplying numbers, these three things happen to end up giving you the same result. In any other type of multiplication, they mean three completely different things. This one is referred to as scalar multiplication. It's the nice one. It's what we normally think of when we think of multiplication, that repeated addition type of multiplication. The dot product is what we think of when we multiply signed numbers, positive and negative numbers. And cross product is what happens when we think about multiplication in terms of finding area. And again, as long as you're talking about numbers, or as long as you're talking about, area of a rectangle where they're all perpendicular, these things all kind of end up being the same value. They're all like 6 in this case. But they're different kinds of outputs and different kinds of multiplication. So we'll need to spend some time talking about that. The nice thing is right now, we'll talk a little bit about dot product on Wednesday. Cross product will wait until you've done some calculus and or physics, because you need to be thinking in 3 dimensions for cross product. Doesn't work very well in 2 dimensions. So we'll mostly play with scalar product and dot product. The only one I want to look at today is that scalar product. What happens when we take 3 and multiply it by a vector, a scalar value multiplied by a vector. So that's why it's called scalar multiplication. And the nice thing is, it means what we think multiplication should mean. If we had a vector v, 3 times that vector v just means take that vector v and do it 3 times and add them together. That's going to give us a new vector that goes in the same direction as v, but is 3 times its magnitude. Just good old repeated addition. So if we have 3 and we want to write it in, say, component form, 5i plus 7j, that would just be 5i plus 7j plus 5i plus 7j plus 5i plus 7j. That would equal 15 i's plus 21 j's. That's why we can just distribute. Fair? So 3 times 5 in the I plus 3 times 7 in the j. So 15i plus 21j. That's your 3v. Just like you'd like it to be. Works very nicely. And that happens anytime you have a scalar value being multiplied by a vector. I say multiplied in quotes because there's different types of multiplying now. We can't just say they're multiplied, but because it's a scalar, a raw value being multiplied by a vector, it has to be good old scalar multiplication. These others come into play when you have two vectors that are multiplied together. That can't mean this vector that many times because this isn't a count. Fair? This 3 said, well, how many is it? V, or the vector u, isn't a how many. It's a how many and in what direction. What does that mean? How does that combine? And how is that different from combining them this way? We'll talk about it. But you got to get some practice with this stuff first. Cool? Okay. Go play with that. Kate, does that give you some more stuff to play with? You said you got to about 4 and 5.
Yes, that helps a lot. Thank you.
Okay, good. Beatrice, anything you need before you go play with that?
No, it's making sense a little. I'm still a little bit confused because I haven't finished reading the book.
Yeah.
I kind of got some of it, but I think I just have to finish it and then practice it as well.
But keep in mind that one thing that I said, a lot of it is presented as if it's some weird new thing because the vocabulary is very new.
Yeah.
But always try to anchor it in, wait a minute, we've been doing this the whole time. We're just kind of using it in a slightly different way and calling it something slightly different.
Different, yeah. Like for
So-
example, like the Pythagorean theorem equation.
Mhm.
Like that one's like, I was like, oh, I know the Pythagorean theorem, but it just looks different what I'm used to seeing it as.
Yeah.
Yeah.
So always, so keep looking for that. Keep looking for that connection to why, oh, this is something we already know. And that can help.
Okay. I also had a question. Are you teaching calculus?
Next fall, you mean?
Well, like, do you mean like winter?
Oh, in the winter. No, I think Annie is.
Annie. Okay.
But Annie's great. So you'll love Annie.
Okay. And is that her like last name as a professor, or is it her first?
That's her first name. It's that's why I call her Annie. It starts with a D. You can look it up.
Okay.
Annie Droulard. There it was.
Okay. All right. Thank you.
Yep. Have a good day.
You too.
You too.